Okay, in the first part of this example problem, we used the graphical representation of two of these forces then to determine what the resultant was. We didn't measure it out to scale. Instead, what we did was notionally draw this out and then apply our knowledge of trigonometry, law of cosines, law of sines, to figure out what R would be. In the component form, what we're going to do is break each of the forces into their x and y scalar components, keeping their direction assigned by the I and the j vectors, those unit vectors in those respective axes. And we're then going to be able to do a little bit simpler math that turns out to be a lot easier for, say, a computer model approach. Okay, so to go get what those components are, what we do is we lay out that vector, and then we consider a triangle that would get formed that would be a right triangle. So that means that this component down here is our magnitude of our x component. And looking at the angles that we've got there, if that's alpha, then our x component for the first one would be its magnitude of 600 newtons times that would be cosine of alpha, which is 45 degrees. Right? So of course it's 0.707, but we'll put it in there. Oops, that was sine. Oh, that's going to turn out to be the same number, but let's be careful here. And so 600 times that, that's 424.26 for that scalar magnitude. Won't worry about as an intermediate how many digits we want to include in this thing. Right? For the y component, then that would be that hypotenuse times sine of alpha, or sine of 45 degrees. Numerically, that will turn out to be the same thing. Now, you could have used this other angle and used a cosine to get that one. There's a lot of different ways to work with that. We won't worry about all that here too much. Right? So that would be the first one, and of course that means that F1 could be then written as 424.26 newtons I plus 424.26 newtons J. Right? Now, same thing can be done with the other one that we looked at. I'm going to draw that a second time. And it's really the same process. There's a lot of different ways that we could go about doing this. I'm going to be kind of a little funny about it for the following reason here. That one, F2, is going to turn out to be 800 newtons, and it's acting from the x-axis at 150 degrees. It was at a what was that? 60 degrees from the y, and that would make it 150 all the way from x. And note, this is going to be kind of funny. We could go and we could say, okay, the x component of this force, we could come along and use this 30 degrees right here. There's your 800. We go 800 times cosine of 30, and that would be 692.8 acting to the left. And so that would have to be a minus 600, well, let me write this all out. 800 times cosine of 30 degrees, but I have to arbitrarily add the negative sign in there to get that to be a minus 692.82. I could have also done that as, this will be really weird, that magnitude times cosine of alpha, 800 times cosine of 150 degrees. When you do it from the positive x-axis, use counterclockwise as positive, you will automatically take care of the sine value that's in there, and times 800. Now, I don't usually do it this way. I like the sort of gut feel approach of just, in a sense, making it up as I go, but then I got to make sure I add the minus sign in there properly. Right? And then you could go F2y 800 times sine of 150 degrees. We should get a positive number there. And we do, times the 800, and that will equal a positive 400. Or we could have done the sine of 30 degrees, gotten it, or we could have done cosine of 60 degrees and kept track of the positive and negative direction on our own. Right? Multiple ways to do it. They're all somewhat equal, but you kind of have to just choose your own path that you like. Okay? Alright, so let's now get this all finished up. We've got a minus 692.82 newtons in the I direction, plus 400 positive exactly newtons in the J direction for that one. F1 plus F2 is going to be equal to our R, our resultant, sum of those two, and so the X component's easy, they both add up. That's 824.26 newtons total in the J direction, and we will have then in the X direction, I'm not sure what I just said, that was the Y direction, 692.82 with a net of minus 268.56 newtons in the X direction. Right, that would be the vectorial representation of this thing, which just goes along with this vector here had two Y contributions that contributed going in the same direction, but the X had one going to the right, one going to the left. There was a net that was much smaller. Looks like the net is slightly going to the left. Right? Magnitude of R then is square root of the sum of the squares, so Rx squared plus Ry squared, and so that would be the square root of minus 268.56 quantity squared plus 824.26 quantity squared. Right, it's the hypotenuse of the triangle formed by those two. And that's a big number, take the square root, and once again we get 866.91, just like we had before. Right? And then, once you have that, let's set this up, because what do we really have here? There's our coordinate system, and we have a component that goes to the left at 268.56. We have a component that is going up at 866.91, and when we draw the parallelogram of those, the resultant is the diagonal of those two components. And so, oh, look at that. There's our magnitude sitting right there. This angle would be, let's call it theta, and so tangent of theta would be opposite over adjacent. And so let's go look what that would be. I don't think I have that right, do I? That's 824.26. 824.26. There we go. 824.26 divided by the 268.56 equals inverse tangent, and that big angle, theta, would be equal to 71.95 degrees minus 90, so the small angle is 18.0 and change. And so we finally would come down to it, just like we had before, that R is acting at 108 degrees from the positive x-axis, and it has a magnitude of 866.9, really 867 newtons. Right? Computer models use the component approach in its math because it's easy to do, easy to set up the equation. There's no intelligence about using law of sines and law of cosines.